All right, so I'm going to pick back up on this example. So finish drawing your diagram, and then this will be 2 widths and 1 length of fencing. Okay, so we have to figure out our equation that we want to maximize. And so we have to look back in the problem that it does tell you to find the maximum area or the largest area of a field that you can enclose. So our equation is going to be the area of a rectangle equation. Right, and we can't maximize an equation that has 2 variables, so we have to use the constraints. And our constraints are dealing with how much fencing we have. So we have 200 feet of fencing to do this fence, and so that's 2 W's and an L add together to give you your 200. All right, so this one's going to be slightly easier to solve for L, because otherwise if we solve for W, we would have to end up dividing by 2, so it'll be easier to do it this way. So we'll just go back and put in that for L, and that leaves us with an equation that has only W. Now, before we find the derivative, we would be smart for us to go ahead and distribute the W. Okay, so we'll find our derivative and find our critical numbers. Okay, so we have one critical number, this is 50. But we need to make sure that this is definitely a maximum. So we'll find the second derivative real quick. And the second derivative is -4, which means that the function is always concave down. And if we thought about it, what this is a quadratic function. If we thought about what it looked like, we would know that that's only concave down. So if there's a critical number, then it's definitely going to be a maximum. Okay, so we want the area of the largest field. So that means that we need to find the length whenever W is 50. So I know that's 200 minus 2 times 50, or 200 minus 100, which is going to be 100. Sorry, you guys might hear my dog clicking around. And so the largest field is going to be 50 feet by 100 feet, or an area of 5,000 square feet. Okay. So calculus comes in handy in agriculture as well. All right, this one is a little more abstract and not as contextual, but we have a rectangle has vertices on the x-axis and 2 vertices on the curve 9 minus x squared. We want to know the maximum area of this rectangle. We are going to do a diagram. So we know what this graph looks like is a parabola open, downward, shifted up 9. It is symmetric about the y-axis. And so the rectangle we're talking about has vertices here and here, which it shifts. So this doesn't have to be the exact rectangle, but this is what they're saying. And then vertices on the x-axis. All right, so this rectangle can get narrower and taller or get wider and shorter. So we want to find the rectangle that has the largest area, either shifting it up and in or down and out. So since we want to maximize area, the area of rectangle again is length times width. And then our rectangle, this point here would be the x value. And since it's symmetric, this point here would be negative x. And so that the width of that is going to be 2w. And then the height or length, whatever you want to call it, this point would be at, the x coordinate would be x, the y coordinate is going to be 9 minus x squared. So the height is going to be 9 minus x squared. So our area of every rectangle here, I don't know why I put 2w, sorry, that should be 2x, is going to be 2x times 9 minus x squared. All right, this is 2x because we have x to the left and we have x to the right. It adds to give you 2x. All right, so real quickly, we will distribute and then find the derivative. All right, and we need the derivative to find the critical numbers. Oops, I forgot my 6. So we get the square root of 3. Let's make sure. I kind of know because I know that, well, no, I don't know. Because that's a cubic function, so we could have all kinds of things going on with it. So let's double check with the second derivative. Okay, so then when I put in the square root of 3, when I do a negative times a positive, that's going to be a negative, and negative critical number, and the second derivative is a relative maximum. And so a question wants the maximum area of the rectangle. So we will just take that square root of 3 and plug it into our area that we got. So it was 18 square root of 3. Oh, wait, hold on. Oh, minus 2 times the square root of 3 cubed. I did this before and got an actual exact answer, but I plugged it in a different place. You can use a calculator. I don't have time to go back and redo it because I know you guys are probably running out of time. Either way, we get this, or you can get a decimal value too. When I plugged it in before to get that 12 square root of 3, I plugged it into this one. All right, now if you are out of time, you all are going to need to watch this example on your own from home. This is an important one. Boxes are really common in optimization problems, but we have a square sheet of cardboard with length 60 inches, and it's folded into a rectangular box with a lid. So it's kind of like those boxes I used to put the calculators in. All right, so for squares with side length x and 2 rectangular regions are just discarded. 4 squares with side length x and 2 rectangular regions are discarded in order to fill the box as shown. So we have the diagram that's extremely helpful. For what value of x is the volume of this box a maximum? All right, so I know that all these little lengths are x, so it's smart to label those. All right, and then I'm going to just go ahead and have this be the width and this be the length. All right, now I know that the way that the box folds over, this right here is also the same as the width. and then one more thing that I know is that this is 60 inches because it's a square box, and so is this. All right, so we have a lot to do. We're going to start off, they went ahead and told you we are maximizing the volume. And so we have to work with several constraints. So to begin with, if we look at the left side, I know, I'm talking about this side right here. I know that if I take two X's and an L, it should add up to 60 inches. All right, and then we're going to want to solve these for L because X is going to be the variable we want in our answer. All right, then if I look at this side, I know that two X's and two W's add up to give you 60. And then again, we want to solve this for X. I'm sorry. We want to solve it for W. X is what we want. All right, so divide 3 by 2. That's W. All right, and then I don't want H either, so the height of the box ends up being this X. So like whatever you're cutting out ends up being the height. All right, so I'm going to take my L, my W, and my H and plug it into V. And you guys are just going to have to trust me that when you multiply these out, you're going to get 2x cubed minus 120x squared plus 1800x. Okay, and then we're going to find the derivative. And we want the critical numbers. So I'm going to factor out the 6 and set it equal to 0 all at the same time. Right, and this factors, not too terrible. So we get two critical numbers. So they're potential maximum, minimum. So we need to find the second derivative real quick just to check to see. All right, so we would want to put 30 in. And when we put 30 in, we are going to get a positive, which means that produces a minimum. But when we put 10 in, we get a negative, so that produces a maximum. Now, it's possible you might want a minimum volume box because you want to not take up very much space. But most of the time you want a box that will hold things. So that means that if you cut out 10 inches from the sides, it will create the box with the maximum volume. So X needs to equal 10 inches for the maximum volume. All right. So on your assignment part of your notes or of your packet, I want you guys to do 1 through 5. And if you want to work ahead and do more problems, you can. But just start off doing half of it. Do 1 through 5 tonight.